So today we are looking at effect of concentration on molar, concentration of solution on molar conductivity. We looked at all other factors. We looked at viscosity, temperature of the electrolytic solution, magnitude of charge, ionic radius, and concentration being a special factor. I wanted us to look at it as a special factor too. I told you to plot graphs, and you tried to plot them. The scales could be a bit disturbing, but you need to choose a very good scale that encompasses all the values that you're always given. Conductivity of one solution, conductivity of the other, and then the square root of concentration. It should be a scale that encompasses all those values. And it's always good you look at the smallest value, which is always a 0. Even if it's not there in the values, the graph will always begin from 0. And then the highest value will always help you get a very good scale. Whether it's a scale of molar conductivity against square root of concentration, or molar conductivity against 1/C, which we call V, or dilution. We have about 4 questions. You try out the others, but I just wanted you to try out the sample ones. Now, I will make a sketch of variation of molar conductivity against concentration on different axes first. And then I'll put it on the same axis later. If I'm looking at variation of molar conductivity with concentration for a strong electrolyte, a strong electrolyte, we can have an example of an electrolyte like sodium chloride. It's a strong electrolyte. All salts are strong electrolytes. That graph will be this kind of graph. You have molar conductivity. Its units are always per ohm centimeters squared per mole, or S centimeters squared per mole. On the x-axis, we don't usually plot their concentration, no. Because the concentration values usually don't give us a good plot. They don't give us a good plot. They are very, very small values. So what we do, we take their square root. And when we take their square root, we get values that are easy to plot. That's the essence of using the square root of concentration instead of concentration on the x-axis. But when you're explaining the variation, then we use the word concentration. That's no problem. Then this is power half. The units of square root of concentration is a moles per liter power half. Now, for strong electrolyte, the graph is usually straight line. It can be a curve, but that curve is slanting that way. It doesn't touch the y-axis directly. To make it touch the y-axis, we do what we call an extrapolation. We extrapolate the graph, and this value here We usually call it molar conductivity at infinite dilution, or molar conductivity at zero concentration. Now this is for sodium chloride, a strong electrolyte. That's the variation of molar conductivity with the square root of concentration. If the electrolyte becomes weak, if you have a weak electrolyte, let's look at an example of a weak electrolyte, any weak electrolyte. We can think of a weak electrolyte like a weak acid. We can think of ethanoic acid. If you have a weak electrolyte like ethanoic acid, I will not still write this word molar conductivity because of space, but still it will be a plot of molar conductivity against square root of concentration. If you're told to plot that graph, it usually come out as a graph we are seeing here. This is moles per liter power half. This graph here comes out as a very good smooth curve that doesn't touch the axis anywhere. Doesn't touch the axis anywhere. I want you to note that. Doesn't touch the y-axis, doesn't touch the x-axis. In case you're simply sketching. For plotting, it would, because of the values that you're given. But in case you're told to sketch, the graph should come out like that. And for it doesn't have what we call molar conductivity dilution. That's why I'm saying it doesn't touch this axis. This is a graph for ethanoic acid. Now, if we are told to sketch the two graphs on the same axis, then we come up with something of this kind. To sketch or to plot, because what we are sketching here is actually what comes out when we plot. This is square root of concentration in brackets moles per liter power half. So there you will have these kinds of graphs. I've told you this one touches the axis at what we call molar conductivity dilution. That's the value there. This is for sodium chloride, and this is for a weak electrolyte, ethanoic acid. So what do you note in both cases? In both cases, you note that molar conductivity decreases with increase in concentration. The molar conductivity decreases with increase in concentration. That's what we do note from these graphs. In both cases, we note that molar conductivity decreases with increase. Molar conductivity decreases with increase in what we call concentration. And then how do we explain those trends? Let's begin with our strong electrolyte. Let's begin with our strong electrolyte. We shall say we are beginning with this graph here and want to explain the trend in variation of the graph. We shall simply say that molar conductivity decreases with increase in concentration. Over as concentration increases, molar conductivity decreases. Okay, so we shall say potassium chloride. Sorry, it is sodium chloride that I have used. I'll begin by saying that sodium chloride for sodium chloride. Molar conductivity decreases as concentration increases. Molar conductivity decreases as concentration increases. Why? This is because sodium chloride is a strong electrolyte. Sodium chloride is a strong electrolyte. If it's a strong electrolyte, so what? That's where the basics are. And that's what I want us to emphasize. For a strong electrolyte, whenever you increase its concentration in a given solvent, let's assume the solvent is water. When its concentration increases, you have very many sodium ions and chloride ions in the solution. And actually, those are the conducting ions, plus maybe those from water. If there are very many, there is what we call a decrease in interionic distance. The ions are so close to each other, so interionic distance of separation decreases. When the interionic distance of separation increases, these ions are going to interfere with their movements, and that's what we call ionic interference. So the ionic interference will increase. When ionic interference increases, then the ionic mobility decreases. And a decrease in ionic mobility leads to a decrease in molar conductivity. So what shall we have to say? We shall have to say that sodium chloride being a strong electrolyte, the increase in concentration of the solution, the increase in concentration increases the number of conducting ions per unit volume. So there are many conducting ions in a given volume. And that leads to what we call a decrease in interionic distance between ions. So interionic distance decreases. Ionic interference increases. And ionic mobility decreases. That's the general trend, but don't stop there. Help us talk about this conductivity here obtained by extrapolation, the molar conductivity at zero concentration, lambda naught. So you continue to tell the examiner that at zero concentration, or what we call infinite dilution. Zero concentration means you've diluted, actually it's a hypothetical thought that you can have zero concentration of sodium chloride in water. That at zero concentration, the ions are far away from each other. the interanic distance is infinite. So that's when the molar conductivity reaches a maximum value. You need to talk about that. At zero concentration, molar conductivity is maximum or reaches a maximum value called molar conductivity at infinite dilution, because what we call ionic interference is negligible there. The ionic interference is negligible. The ions are far away from each other. So you add that to your explanation. So you say at zero concentration, or what we call infinite dilution, molar conductivity is maximum. When you look at your graph, that's the highest value we have, although it's obtained by extrapolation. Because when you talk of infinite dilution, it means ionic interference is negligible. Ions are far away separated from each other, because ionic interference is negligible. So if ionic interference is negligible, the ions are free to move at any speed they want, and the conductivity is maximum. Hope that's very clear. How do we award marks for this? Molar conductivity decreases as concentration increases. Sodium chloride is a strong electrolyte. Increase in concentration increases number of conducting ions per unit volume. Interanic distance decreases, ionic interference increases, ionic mobility decreases. At zero concentration, molar conductivity is maximum because ionic interference is negligible. That's 4.5 marks or less, depending on the awarding of someone marking you. So that's for a strong electrolyte. Whether the graph is separate like this or if it is incorporated on the same axis with another one, you give that same explanation. You can have many other strong electrolytes other than sodium chloride. How about for a weak electrolyte? I remember telling you when I was talking about electrolytic conductivity, that for a weak electrolyte, we talk of the degree of dissociation in relation with the number of conducting ions, and nothing much about it. There we don't talk about ionic mobility, ionic interference, such things, and its explanation is the simplest. So for a weak electrolyte, molar conductivity decreases with increase in concentration. Why? Ethanoic acid is a weak electrolyte, so that as concentration increases, when you increase the concentration, the number of unionized molecules of the acid in solution increases, and that leads to a decrease in number of conducting ions per unit volume. Remember me explaining that, but I can still do it. The equilibrium established is this. In water, this being an acid, water acts as a base. It donates a proton. It accepts a proton. This is an acid. So water acts as a base in such a solution by accepting a proton. When it accepts a proton, it becomes hydrozonium ions. So if that's the case, we're having a solution of ethanoic acid. Remember, this is weak. And being weak, it's only partly ionized. That implies that in each solution, there are very many unionized. When you increase the concentration, of the ethanoic acid, that means you're making a solution having very many unionized ethanoic acid molecules. the conducting ions are very few in that solution. So when very many of these are unionized, that means the number of conducting ions per unit volume, number of these ions is low due to the decrease in degree of dissociation of such a solution with the increase in concentration. So whenever concentration increases, degree of dissociation decreases, and the number of conducting ions per unit volume of solution also decreases for a weak electrolyte. So what shall we have to say? For ethanoic acid, which is this one here, increase in concentration decreases the molar conductivity. Decreases the molar conductivity. Why does the molar conductivity decrease in that case? The molar conductivity decreases because I've talked about increase in number of unionized molecules, which is as a result of a decrease in the degree of dissociation. So that decreases the molar conductivity because the degree of dissociation alpha decreases. Number of unionized ethanoic acid molecules decreases. And the number of conducting ions per unit volume decreases. So something I've forgotten to talk about. You must mention to us that ethanoic acid is a weak electrolyte. Must talk about ethanoic acid being a weak electrolyte. So what do we have? Increase in concentration decreases molar conductivity. Ethanoic acid is a weak electrolyte. Degree of dissociation decreases. Unionized molecules number increase. Number of unionized ethanoic acid molecules increases. Most of the molecules of ethanoic acid are unionized. The number of conducting ions per unit volume decreases. So that's the effect of concentration on molar conductivity. In our question 1, that's the kind of graph I was telling you to plot. It was a graph of, actually on the same axis, we are taught to plot graphs of molar conductivity against square root of concentration for ethanoic acid and potassium chloride. Mary, did you plot the graph out?
Yes, teacher.
Send it to me on WhatsApp. So if we look at those graphs, the one of Muhammad is already here. When you look at these graphs, I guess this is the first graph that you had to plot, Ahmad, are you seeing your graph?
Not yet, teacher.
Okay, so this graph here is a graph you are plotting for molar conductivity against square root of concentration. So when we look at this kind of graph, I see the axes are okay. This is correct. Even this is correct. But I don't see the units for molar conductivity. You forget them. Would have forgotten those units for molar conductivity. You must show the units as per ohm centimeter squared per mole. Now, yeah, they are there. I've seen them. They are here. So that's fine. Then this is for potassium chloride. You don't need to indicate lambda C again here. You simply write the word potassium chloride because we are already aware that on the y-axis we have variation of molar conductivity. So you simply write potassium chloride here as a word and try to make this curve very smooth. When you touch the pencil and try to draw the curve, don't stop. You see, you stopped here. Don't stop. Just draw the curve smoothly and it flows. Then here, you had to do the same. Get the pencil, draw a smooth curve, but otherwise your graphs are very fine. Maybe the writing here, you labeled this upside down. Just write the word ethanoic acid very easily here. Ethanoic acid on the curve. Or you can write it here and show an arrow that this is a graph for ethanoic acid. So that one was very fine. You see these values are bigger. Otherwise, if we had to plot graphs of concentration instead of square root of concentration, the graph would a bit disturbed. So I wanted you to draw this graph so that you practice. You practice the scale because the scale usually disturbs, and yet after plotting them, they can easily be explained. So that's all about the first kind of graph. You always have graphs of that kind if they are to be plotted and not to be sketched. And the explanation is the same explanation I've just given. If you want to obtain molar conductivity at infinite dilution here, then you extrapolate this curve here. Extrapolate it to the y-axis and read off that value in case you're asked. So here you are told to complete the table. Must show the table being completed. Plot the graphs on the same axis. In case they say separate axes, you do the same. State explain the shapes of the graphs. That's what we have just seen. Then, for the second graph, we shall see it after making the explanation for it. We shall see it after making the explanation for it. Otherwise, that was a good plot. So let's see another concept. Instead of using concentration, we may sometimes use what we call dilution. We may sometimes use what we call dilution. Yeah, I've seen your graph, Mary. It's fine. It's fine. So the kind of graph you have is this one. So this is your graph, and it's also a perfect graph. However, the scale disturbed you on the y-axis. I'm seeing a scale that is disturbing. You need to choose a better scale than this. Could use a scale of maybe 12, then from 12 you go to 24, something like that. 12, 24, other than these points here. On the x-axis, still I see you have problems with scale. Though you plotted the graph, but you have issues with scale choice. You choose the scale you choose, you chose disturbed you. I know it disturbed you when plotting. So you'll have to find a way of choosing better scales. Then even the lines, when you're drawing these lines for the axes, try to use a ruler. So without wasting time, let's go back to the variation in molar conductivity with dilution now. When I talk of dilution, I mean the reciprocal of concentration. Which is 1/C. And for it, the units are moles per liter per -1. Moles per liter per -1 is the same as per mole dm cubed now. It becomes per -1 and this becomes per positive. Per mole then decameters, decimeters cubed. Sometimes the dilution can be given a letter V. Sometimes you can give it a letter V. Now, what happens for dilution? For dilution, the opposite is true. The opposite is true. Let us see what happens. If you plot a graph of molar conductivity against dilution for each of those electrolytes, let's first of all look at the graph of molar conductivity per ohm, centimeters squared per mole. This is dilution, or you can call it 1/concentration. In units, mole dm cubed per -1. And I'm beginning with a strong electrolyte now. If it is potassium chloride, the graph will have to be this kind of graph. It will have to move like this. It doesn't touch the axis anywhere. I want to make it more smooth. So it will have to be this kind of graph. So in case you get that kind of graph, you still extrapolate it. This is for potassium chloride, a strong electrolyte. In the previous case, that of potassium chloride was almost a straight line. Sodium chloride was almost a straight line, slanting downwards. In the case of dilution for a strong electrolyte, it's a curve sloping upwards until you obtain a maximum. And to obtain the molar conductivity at infinite dilution, we do an extrapolation to read off that maximum value. That one there becomes your molar conductivity at infinite dilution. I still emphasize that for these graphs, you plot them beginning from 0 on both axes, and then this curve here, in case you're sketching, it doesn't touch the axis. Doesn't touch the axis anywhere. Then for a weak electrolyte, for example, let's assume we are using propanoic acid, a weak electrolyte. The graph will be this kind of curve. It will be almost a straight line. It also doesn't touch the axis anywhere. In case this is our weak electrolyte, propanoic acid, it can be ammonia, it can be any other weak electrolyte. But that's the kind of graph you come up with. So in case you come up with that kind of graph, you can still explain the same way. Actually, the explanation doesn't change as that of square root of concentration. Okay. So just have to know that it's the opposite of the other. Let's begin with the potassium chloride. So what happens for potassium chloride? For potassium chloride, we are seeing that molar conductivity increases with increase in dilution. Up to a maximum value. You see that from the graph. Up to a maximum value. Molar conductivity increases with increase in dilution up to a maximum value at which it remains constant at infinite dilution. That's the trend that we have to explain. I've said potassium chloride molar conductivity increases with increase in dilution up to a maximum at which it remains constant. And that maximum is occurring at what we call infinite dilution. Hope that's right. So if it remains constant at what we call infinite dilution, how will you explain that trend? We are diluting a solution, and that's why the conductivity is increasing. When you dilute the solution, the ions that are so close to each other in a concentrated solution begin to separate. They begin to separate within the solution to have that interionic distance of separation increasing, ionic interference decreasing, and ionic mobility increasing. Okay, so that's what we have to explain. So you say as dilution increases, interionic distance increases. Distance between ions increases. Ionic interference decreases, and ionic mobility increases. Then we talk about this molar conductivity at infinite dilution, which we call zero concentration, as we saw for the x-axis having square root of concentration. So at zero concentration, what happens? the ionic interference is negligible. The ionic interference is negligible, and that explains why we have said this. Why we have a maximum value which remains constant at infinite dilution is because the ionic interference at that value is negligible. So in both cases, molar conductivity at infinite dilution is obtained by extrapolation. Okay. However, there's something I forget. Don't continue forgetting it. Mentioning that this is a strong electrolyte in your explanation as you begin explaining. Then how about for ethanoic acid? I mean propanoic acid. So for propanoic acid, still the same trend. Molar conductivity increases with increase in dilution. Why does it increase with increase in dilution? Tell us that propanoic acid is a weak electrolyte. And so what? As dilution increases, the increase in dilution does what? Increases the degree of dissociation. So when the degree of dissociation increases, ethanoic acid is dissociating at a faster rate to give us very many conducting ions per unit volume. And the number of conducting ions per unit volume increases. So that is basically that for concentration. That's basically that for concentration. Still, if we look at a few graphs or some graphs that I look at that, first of all, the one plotted by Humbert. So your graph is here. Let me share it in a new tab. When we look at this graph, still I will emphasize the same things I've talked about. We see that you have a plot of molar conductivity against dilution. What I want you to avoid is writing the lambda C again. It's already on the y-axis that this is conductivity, molar conductivity. So you simply write the word that this is hydrochloric acid and the other one is for ammonia. Then you go on to explain the same case. Ammonia is a weak electrolyte. Go on to give the reasons about degree of dissociation and conducting ions. Then talk over hydrochloric acid and say it's a strong electrolyte. Give the reason. In case they ask you molar conductivity at infinite dilution, you extrapolate this graph and read off the value there. It may be important. Actually, you may follow that with some calculations where you could be using it. So that's all about that. Can I plot 0.3 as 0.0? No. I think the scale, you must choose a scale that simplifies your work. Plot that value. You choose any value near 0 on your scale, near 0 around there. So you may not plot it as 0. However, I don't see any problem with these graphs. They are fine. But according to this scale, actually, it would end up being a 0, according to this scale. So this is a correct graph. The only problem is the labeling I see here. Then for the other graph that I want us to look at is this one here. I want us to look at another graph. So the other graph is the one by Mary, which is here. Yeah, these are very good graphs if you they examine your graph plotting skills. If you try to give them some good time. For this one, we have the graph of molar conductivity against dilution for hydrochloric acid, which is there. And then for ammonia, I don't know why here it is doing something like this. There could be a problem in this region. There could be a problem with plotting in this region here. But I think the rest of the work looks fine. So that's how you plot the graphs and explain in the same way. So you'll try out other questions from Mystifying Physical Chemistry and get a good practice about those graphs.